Speaker is Dr. McKubre.
In the interest of time, I was going to give you a 3-minute lecture on electrochemistry. I'll reduce it to 30 seconds. The hydrogen evolution reaction to deposition of hydrogen and deuterium on surfaces, particularly platinum, is extremely well known. It's so well known that the reactions have names and the names have faces, which will appear on my next slide. The problem is, as we discovered early on in this business, it's great. It works very well for platinum. It doesn't work well enough for palladium. So fundamental electrochemical studies need to be continued just to understand how we deposit our hydrogen ions onto our palladium surface for it to do the things that we're here to talk about. Obtain excess heat by obtaining high loadings and obtaining high flux conditions. The need for flux became first apparent to us adventitiously, really. We saw this result in 1993, maybe 1994. Loading. This is a cell that happened to be in a helium leak-type vessel M4, and we saw excess power in a couple of bumps, and we tried to understand, where do these bumps come from? What we noticed was the resistance ratio, X versus the time in this plot, X, oscillated. It seemed like noise, but it isn't noise. And when we looked closely at this, it was a periodic fluctuation of loading. The period about 2 hours. The amplitude of this periodicity changed and affected the excess power. The excess power, this is where the equation that Francesco Celani spoke about yesterday, thank you, Francesco, came from. And the amplitude of this fluctuation, of course, this is loading and unloading, loading and unloading, and the electrodes were breathing all by themselves, sort of sucking in deuterium and expelling deuterium with a period of about 2 hours. And to do that, of course, you have to have a large flux of deuterium through the interface, and we discovered entirely adventitiously that the excess power is proportional to this flux of deuterium through the interface. So it's a resistance ratio versus a loading curve that I am so fond of. We set out to try and do that deliberately. So we said, okay, great, brilliant. We finally understand, why is excess power so variable? It's so variable because this flux condition is variable and uncontrolled. We can control it. We're electrochemists. We're masters of our experiments. So we set out to discover a perturbation function, modulation of current or voltage or both, that would allow us to both maintain the high loading condition and the high flux condition. And the problem quickly became apparent to us because it's a non-linear response process. What you gained on the upside, you more than lost on the downside. So you could fluctuate the loading of your surface fine, but always with a result of net loss of loading. So you get a high modulation, high flux condition, but you couldn't have a high loading condition. You couldn't have both things simultaneously by any waveform that we thought of ourselves. The solution to this problem came in the strangest of ways with a function that Irv Dardick announced to the world in 2003 at the Cambridge ICCF-18 meeting, which of course I didn't believe. I'm an electrochemist. I know how to load hydrogen into materials. This is my field of expertise. We do it DC. We control everything as well as we can. Modulations are always going to be bad. and a crazy modulation like this is going to be very, very bad. Being an empiricist, however, crazy as it may be, let's try it and see. And it turns out to be right. And the only waveform that I know to this day that is able to both obtain the high loading and the high flux condition is this superwave. Now, the superwave is not well defined. There are many, many forms. It needs to be studied with more care. But this is an example of the resistance ratio versus loading curve that I showed on the last slide. So you go up, you go down, but load, load, load. The red is the loading. The loading here is now up at about 0.98, which is very, very much in the regime that we're interested in operating in. The dots here are the mean, the maximum, and the minimum loading in the 20-minute period of this superwave. So what this electrode is doing all the way up is loading and unloading, and the variation of the maximum and the minimum from the mean is the dynamics of deuterium going in and out through the surface. So we've obtained a high flux and high loading condition. Many, many milliamps of deuterium flux through the interface. It ain't easy. I really thank Vittorio for his introduction to electrochemical impedance spectroscopy. We, in 1989, this is my field of expertise, or was before I became one of you. So we applied this technique in a pressurized cell, not easy to do, and we obtained these results. This imaginary is capacitance, real is resistance. I presented this at the first International Conference on Cold Fusion, ACCF, in 1990, data obtained in 1989. This is what Vittorio described as the normal response of a normal electrode, an RC semicircular effect centered on the real axis. And what we had for an active excess heat producing cold fusion experiment is this, what's called an inductive loop. The resistance going back here is a negative resistance, often modeled as a inductor. When I produced this slide in Salt Lake City, 1990, early, Martin Fleischmann's eyeballs bulged up, and he came up and seized me and says, what did you do? How did you get this result? He was very, very fascinated with this result, because what this is demonstration of is an oscillatory relaxation process at the interface, which seemed then to be critically coupled to the evolution of excess heat. So again, how do you do it? And we're electrochemists, we're masters of our environment. We can do whatever we want to do, except we can't. So I did this work in 1989 and 1990 and was distracted heavily for 25 years, and I'm a little lazy. We were distracted heavily by the demonstration of the effect, continued replications of more examples of excess heat which didn't really teach us anything, rather than its definition, understanding the cause of this effect. And we're just looping back to that now with Vittorio's help and Dr. Antonio Lagata, who has the instrumentation, developing new instrumentation to allow us to interrogate these systems real-time under excess heat conditions. And partly it's taken 25 years because we needed technology to catch up with our need. It ain't easy, and it does take money. Vittorio showed this already. Fortunately, data obtained very recently, this month or last month or something, at ENEA Frascati, where rather than I think if Vittorio had carried on to lower frequencies, this thing would probably have come around here too. But he did uncover oscillatory terms. So this is an active heat-producing cathode that has an inbuilt oscillation. This system has its own flux dynamics. In this case, the characteristic frequency of that was 166 Hertz. So where do these oscillations come from? We shouldn't really be surprised. This whole electrochemical system is not a DC system. It's a system of coupled oscillators. I don't have time to go through every one of them, but if you just start thinking about the D2O molecule, The molecule dissociates and reassociates. There's an oscillation just backwards and forwards along this line. The deuterium ion is not free in the solution. It's surrounded by a sheath of water molecules. These water molecules have to be removed in order for that ion to associate with the surface. So there's an oscillation of the situation of this ion in its hydration sheath. The modulation that I showed you between the D plus and the D adsorbed, which is affected by the superwave. Superwave also affects other terms. There are mass transfer terms that are oscillatory in nature. The absorption is not static. An atom enters the lattice and leaves the lattice. There's a dynamic, there's an oscillation in this, and there's the 2-hour breathing mode data that I showed you, which is a function of dimension, of course. So all of these processes.
So which one is 166 hertz?
It's electrochemical. Electrochemical. It's an electrochemical kinetic one. It's a third one. Is 166. Now we know what that is.
Okay, what's the third? Go back.
No, I don't have time. So. Vittorio has covered a lot of this. What is the role of metallurgy in controlling this flux dynamic? Vittorio at previous times has done a beautiful job of explaining that the diffusion of the atom into the bulk material doesn't follow Fick's law. It doesn't follow Fick's law because the lattice expands. The expansion, if you like, thinking in simplistic terms, the system is being squeezed and pushed, and it says, I don't like this, and it pushes back. So you can develop a condition where, although you have a concentration gradient, you don't have any flux because the mechanical force is pushing back against you. You can trick this with oscillations. You can push on it and sit until it says, ouch. You back off, and it thinks, all right, I'm free, and then you hit it again hard at the right time, and you can trick the system into loading faster by using these dynamic systems. So much to do, so much to think about. In addition to control of the bulk metallurgy, we need to control an awful lot of things. To control the electrochemical kinetics, you can add additives designed to do specific things. Increase the kinetics, block the sites of recombination. Vittorio talked about platinum. Platinum is good for texturing and very bad for loading because platinum will discharge the hydrogen species preferentially and form bubbles, which takes your carefully produced atoms away. Emergent grain boundaries are a problem. We found very early in this business that two elements only improved the loading, aluminium and silicon. These go to the grain boundaries, block the emergence of carefully loaded deuterium, which finds its way to the grain boundaries and comes out down that grain boundary river. Poisons. 1/3 of a monolayer of certain elements a third of a monolayer of certain elements will change the electrochemical kinetics by 3 orders of magnitude. A third of a monolayer is less than 10 to the 15th atoms per square centimeter. So we need to control those bad guys at better than 1 part in 10 to the 10th, since you have more than a mole of solution in your system. I'm speeding through a otherwise larger talk. But we need not only high loadings, we need high flux. You can actually get very good loadings of hydrogen and deuterium into palladium. In fact, Peter Pfeiffer gave us a lecture this morning with the use of boron. Boron is a great way to get high loading because it sticks the surface up, it constipates the surface. You can shovel your hydrogen in and then put boron in afterwards and you lock it up tightly in the bubble. But you change the flux conditions such that you achieve high loading but very low flux. So you need both of these two things together. That it's hard. And whoops. And I could speak much more to this, but just think about the effect of temperature. In order to get high loading, you need low temperatures just because of the phase diagram. In order to get to high flux, you need high temperatures just because of the kinetics. So these two things push against each other. It's a Laffer curve. There's an optimum temperature that you need to achieve probably for each piece of metal. How do you find it? Well, you have to do experiments. You have to study these things. You have to not only apply inputs, you have to apply 5 more minutes. Well, that may be more than I need. This is my last slide. So what is the goal? In systems where interfacial dynamics, periodicities, and bulk loading are important, you'd like to interrogate resonant frequencies of critical elements. That is, we like to put in a spectrum of signal, measure a spectrum of response, and understand the transfer function of the system. And this is precisely what Vittorio and I and Tony Legato are attempting to do. Have some hardware that will allow us to gain information from our experiments and not just, is there heat or isn't there heat? Preferably, we like to do this with a minimum, preferably zero perturbation. You can use electrochemical noise for this purpose. The system is already noisy. You can process that noise information in order to gain the knowledge that you need about these various oscillatory processes. So the dream, develop some sort of positive feedback, pulse the system, see how it responds, interrogate the system to see what it's doing, and feed it the signals that it needs in order to modulate the response function, modulate the heat. Ultimately, not only producing heat, we're going to need to control it. We're going to need to know what it responds to, and we're going to need to deliver whatever the system requires electrically on demand. And the only way we can do that is to listen to the system and see and know how it responds to certain frequency components. In the end, modulate the rate of heat production, achieve results that are controllable, reproducible, and hopefully valuable. Thank you for your time.